All right, and I like that concept. The social starts when it starts. So I think we'll be okay on that. And again, from me too, thank you very much for being patient on all this. This is a new venue, and it is a really amazing place to be. One of the things I've been noticing out there, which has been key, is that a lot of random people from the community are getting aware of this. This has not happened in a long time, and that's definitely helping us. So this is an ideal venue from that standpoint, and I'm willing to put up with some of the glitches just because of that factor. Another thing is many of these random community people are young people, and that is vital to our future. They are our future, and they're starting to find out about us. I have had some amazing conversations with some members of the public today. Okay, without further ado, our next speaker, Ron Nott. He's spoken at a couple of these since 2004, and he's somebody who's impressed me as one of those real practical visionaries. He was a power engineer for many, many years, he says in ancient times. He's also been a broadcast engineer since 1960. He used to work radio, and in 1982 started his own manufacturing business, making antennas and lightning protection and other things like that. By the way, that business is currently for sale. I want you to know that. So here is Ron Nott.
I got it. Is it working now?
Okay. Step over here.
Okay.
Okay.
I turned it on.
Okay.
What else is
Should
there?
be good to go.
Okay.
Actually, we'll just stuff that right in there.
Okay. Okay. This is about lightning and how you can protect yourself from it. Your person, your property, everything. Everybody has a lightning experience. Need sound a little higher? Sound a little higher, John. Yeah. Okay. How about now? Are we doing good in the back there? No, he says it's a little more, John. Are we there yet? We're starting to ring a little bit now. Okay. Are we all right? Okay. Again, this is about lightning and how you protect yourself from it. And to understand how to get away from lightning, to protect yourself, your property and everything from it, we really need to understand what it is, where it comes from, where the power's from, and all that stuff. And so what I have done, I've entitled this talk, Life in the Great Capacitor, which sounds a little strange, but we all live in a great big capacitor. Let's see, did that, okay. Need to go to this camera here, John. Okay, is that the symbol for a capacitor? A really big one. But, pardon? Well, to hold everything, in a minute I'll tell you about what's in there. This is a capacitor. You've never seen one like this before. And so I also have this picture of an ant. Oops, he's upside down. I was going to draw a bunch of ants across this bottom plate of the capacitor, but I'm not a very good artist, so this will tell you what the ants would look like. And the ants represent us. We live in this capacitor. And as you know, in between the plates of a capacitor is what we call a dielectric. Now, so it can be all kind of different materials. It can be air, and it can even be a vacuum. But the point is, what is in there is an electric charge, an electric field. And what this capacitor is really, if I identify these, down here is Earth. Oh, okay. Okay, this is our good old surface of our Earth here. And up here is the ionosphere. Pardon? And we put little dots up there which represents all the ions that are in the ionosphere. Sorry if it's a little fuzzy, this camera just won't quite focus for us, but the whole idea is we're down here on Earth. This is a plate of a capacitor because the Earth is a conductor. It's not a real good conductor, but it's a conductor. Up in the ionosphere, the same thing. It conducts electricity, but not really well. But in between us is this space of somewhere, depending on which expert you talk to, 100 or 200 kilometers in distance. And so if we look at the charge, normally on a nice sunny day like it is outside right now, the surface of the Earth is negative. Relatively speaking, and bear in mind that's an important word, relatively the ionosphere is positive. So there's a tiny current because the air is ionized. But first of all, the experts estimate there's about 120,000 volt charge from here to here. But that's a big number, but at the same time it's spaced out over such a long distance that it's not really big. Oh, did that work? Oh, good. All right, helped. All right. What scientists for years have done is they say, well, there's a gradient, a voltage gradient from here up to here. And in a nice sunny day like it is out here right now, the gradient is about 100 to 200 volts per meter. Every meter that you elevate, it's about 100 or 200 volts. Now the energy level is very low, so you don't get shanked. Well, if my appear at 200 volts, it could be dangerous, but it's not. And so this is the normal thing. And what's in this space in between, it's not a perfect insulator because there are free ions, there's water, there's all kinds of stuff through which electricity can flow. And what happens is, this, like I say, this is fine weather. What happens is if a cloud comes in, flat bottom cloud, fluffy cloud like that, everything changes. And I'll get into that. I better look at my notes to make sure I don't mess up. Well, we did the first page. Okay. Now, this, believe it or not, the bottom of this cloud to the Earth also forms another capacitor. So we could draw another little capacitor out here at the side that would be equivalent to this. And everything is different now because, first of all, the formation of a cloud, it turns out that a cloud is like a great big battery or a big wet capacitor, if you want to look at it that way. This thing becomes charged, and there are actually 6 sources from where the charge comes from. The most important is cosmic rays. Back over 100 years ago, that was a big deal to scientists, looking at cosmic rays. These are particles that come in from outer space, from all directions. That's why our ionosphere is up there. These particles wind up charging that up there, and fortunately, there is enough stuff up there to slow those things down and absorb enough energy that not too many of them come down to the Earth where they could damage us. The best way that they've come up to describe these particles, which is cosmic rays, imagine an atom, just the nucleus, and all the electrons have been stripped off. And let's say it had an atomic weight of 25 or 30, and you have this nucleus of protons and neutrons that's whizzing along at almost the velocity of light, probably over 99% of the velocity of light. No electrons. So it comes in and it enters our atmosphere, and it bangs into our air atoms and molecules, and each time it hits, it knocks some of them apart. Well, this creates more ions because now, even if they only knock the electrons off, you've got free electrons floating in space, and then you've got positive charged atoms, the rest of it, and these accumulate. And somebody has estimated how many there are, and it's way up in massive numbers. And one of the things that I'd like to point out about this, don't try to memorize numbers whenever you're looking at studying lightning. It is such a dynamic, complex process that typically whenever you hear a talk on lightning, they're going to tell you how many thousand amps are in the strike and how many volts it takes. Don't waste time with that. It's really impressive in big numbers, but then as soon as you leave, you're going to forget all those numbers. So the idea here is to understand what is happening. As the air gets denser, more collisions occur and more secondary electrons are formed and molecules are knocked apart. And they're called secondary ions. And I think that sometimes they say that one atomic particle or one of these particles coming from outer space can create up to 40,000 to 50,000 secondaries. Well, that means the whole place is all this space in here is now full of ions. Now, what happens is our cloud down here, it's composed of droplets of water, fog droplets, cloud droplets. And what happens in these things is that the water droplets catch a lot of these ions. And so after a period of time, these accumulate enough so that the water droplets are all charged. They become little capacitors in themselves. And if we were to look at one of these droplets real closely, we might see that it's got a bunch of positive ions in it and a bunch of negative ions both. And let's say we had 10 positive ions in there and 15 negative ions, that water drop would have a net charge of -5. What happens then is all of these droplets are charged, and the sun, effectively, the cloud looks like it's boiling, the shape of it. And what is happening is, and the scientists don't know for sure why yet, but the positively charged particles wind up going to the top of our cloud, and the negatives go to the bottom. And so after a period of time, it looks pretty much like this. And bear in mind, it's not perfectly positive at the top and perfectly negative at the bottom, but a voltage of millions of volts can develop in here. We think, well, if we have both positive and negative ions floating around the air, they are going to neutralize because they're going to stick together. The opposites are going to attract. They do. It just happens that more come in than can be neutralized. And so the net result is it simply continues to, we continue to have all of these ions in the air. Okay, the bottom of the cloud flattens, if you notice from a distance. You will see this. And I have this theory that what happens is it is equalizing, and it's becoming a flat capacitor plate right there. That may or may not be right. One thing I need to point out is where before we said that the Earth is negative and the ionosphere is positive, that's correct, but when the cloud comes in and the bottom of this cloud gets all charged negatively like this, everything turns upside down. So you have this extremely powerful negative charge at the bottom of the cloud. The Earth, relatively speaking, and remember that word, relatively, it turns upside down. Now it's positive. And indeed, whenever most lightning is called a negative strike, not all of it, and there's reasons for that too. I'm sure that all of you have been traveling somewhere at night, and you look off in the distance and there is a big thundercloud. And where you are is pretty nice weather, but there's a big cloud in the distance. And from time to time, lightning will flash. And it's inside the cloud. And we call it sheet lightning because it looks like a big bed sheet hung up in the sky. And so that's the physical appearance. But what's really happened there is there's a discharge between the top and the bottom of the cloud. And that's called intra-cloud lightning, inside the cloud. Fortunately for us, about 80%, and some people estimate more or less, but a large part of lightning is intra-cloud, which means that it doesn't come down to zap us here on the Earth. It has other effects, this stuff. You may have been listening to AM radio or shortwave radio, if there are any radio amateurs here, at night, and you hear these static crashes on the radio. What that is that's this discharge inside these clouds, and bear in mind this can travel hundreds and even thousands of miles. And a lightning flash is a very broadband radio signal. It's, the old saying was, well, it's DC to light, but it pretty much is. It's from very low frequencies clear up through light frequencies. What we are mainly concerned about is cloud to ground, because that's where the damage occurs whenever we get a strike from a cloud down to the earth. Whether the way I got started in manufacturing lightning prevention products 26 years ago was I have been in broadcasting for a long, long time, and broadcasters, all broadcasters, you've got something sticking up in the air. I don't care if it's AM, FM, or TV. You've got something sticking up in the air that's going to get hit by lightning, and it's going to damage an antenna or come down the transmission line and damage the transmitter inside the place or damage a receiver or something. There are all kinds of things that can happen. So I got real interested in atmospheric physics and started into that. And I lost my train here. At any rate, the cloud to ground is what's important. Now, as I said a while ago, in this circumstance over here, we only have about 100 to 200 volts per meter of rise. Whenever this happens, you can get up to, it'll reverse polarity, and you can have thousands of volts per meter. And in fact, the lightning researchers in Florida, and there's also a lightning lab down here at Socorro, New Mexico, associated with New Mexico Tech, they find that you can have 8,000 or 10,000 volts per meter. Now, if you've ever been out and you felt it tingling, if there's a thunderstorm nearby and you felt tingling, or if there's a lady present with long hair, the hair will lift, you're into a field like that, and that's an electric field. You cannot get around the fact that there's an electric field there, and it's composed from the bottom of the cloud to the earth can be up 10 million or more volts. And that's how we can have this 5,000, 10,000 volts per meter. They have instruments in Florida where they do triggered lightning that measure this electric field, and they find that whenever it gets above about 12,000 volts per meter, they fire a little rocket up in the air with a little thin wire behind it, and it will trigger a lightning strike. And that way they can do all kind of measurements to a lightning strike and the size and all this stuff. And it's kind of curious. Somebody years ago said, well, that's a little thin wire. How can it carry a 10,000 amp lightning bolt? It doesn't. All it does is ionize the channel and starts the lightning strike to make it go. There's another factor, and I thought I invented this, but apparently not. If you, I'm sure you all watch the weather on TV, and they have things called isobars. And an isobar, by definition, is simply a line that connects all points of equal pressure. In lightning, let's say we have a cloud here, and again, it's one of these big cumulus clouds, and now we can look at this, and I'm going to look over here where it's really flat first, and these lines would be fairly uniform, and we could, every meter we could measure this, and when it's really a severe storm, we could have from 5,000 to 10,000 volts per meter. But what happens is, let's say if you have a tall structure, let's say like a tall communications tower, so let's say 300 feet tall, these lines, these isoelectric lines, mold themselves around this tower like this. And what you'll see is, because of this tower sticking up in the air, they get close together near the top. This means that the electric field is much more intense at that point, and that's why lightning will hit the top of this tower instead of coming down to ground over here. And you can't say that's always going to happen because there are so many variables in lightning. I'm inclined to believe that this is the reason why mountains have more lightning than down here in the flatlands. It is known that there are more thunderstorms and more rain up in lightnings up in the mountains because of the high elevation and the concentration of the isoelectric lines. I mentioned here that tall guys are more vulnerable to us than us short guys, because if you have you're in a field and it's 8,000 volts per meter, and you're 2 meters tall, which is a little over 6'6", like Vern over there, wherever he went. You're much more likely to get zapped than us short guys. I have to go back to Benjamin Franklin now. We're going to talk about protection and how you do that. Benjamin Franklin was quite a brilliant man for his time, but some people tend to discredit him nowadays and say, well, he didn't know much and he made mistakes, and you shouldn't have used that kind of pointed rods. But he's the first person that did a paper that said this is electric. He wrote a paper in somewhere 1750, give or take a few years, to be presented at the Royal Society in London. Now, at that time, at 1750, the Royal Society was the premier scientific institution in the world. And, so those people were perhaps kind of snobbish sometimes. They obviously had some big egos. So a friend of his, he couldn't go, so a friend of his went over there and gave this paper. And it had a funny title. It was on the sameness of lightning and electricity. And so this guy went over there and read the paper, and they all laughed. And within 10 years, they said, oh no, he's right after all, because he proved it, and then other people began to prove it. And I don't know what they did to explain lightning then. Of course, going back to Greek times, they said, well, it's the vengeance of the gods. They don't like us, so they're going to zap us with lightning. And there were all kind of negative things about that. But bear in mind that in Franklin's time, we didn't have radio towers sticking up. All we had was houses and barns and church steeples. And church steeples got hit quite a bit. Over the years, we furnished prevention equipment to go on church steeples on several occasions. And I'll explain how this works in a little bit. But one of the things that he did, he said that there is a silent current coming off of a sharp point. I'm sure you've all heard of the Leyden jar. Sometimes it's pronounced Leyden jar, but it came from the University of Leiden in Holland in about 1730, a few years. And that's what got Franklin interested in the study of electricity. He built his own. Now, you stop and think about a Leyden jar. A Leyden jar is just a very, very primitive capacitor. It's the first capacitor that there was. Today, students make them by taking a glass beaker, and they will wrap aluminum foil on the outside and aluminum foil on the inside, and those form the two plates of the capacitor, with the glass being the dielectric in between. And that is the fundamental principle of the Leyden jar. But you have to stop and think about, where did they get the electricity from to charge those Leyden jars back there more than 250 years ago? Static electricity was the thing. You've probably heard about the monks getting charged up and discharged. This one king liked, they would generate a lot of static electricity by rubbing fur on a sulfur ball, and he'd zap a whole ring of monks standing in a circle, and they'd all jump precisely at the same time, because as the charge went through, they all got the charge at the same time. And he thought that was pretty humorous, had him do it over and over. The point here is the voltage was very high. Now the current was very low, but the voltage was very, very high. And if you don't think it was high, think about on a dry winter day, you walk across a nylon or synthetic carpet, you reach out and touch the doorknob, you get zapped. How much voltage is that? It's estimated between 25,000 and 35,000 volts. Well, how come it doesn't kill you? Because the current is in microamps. It's extremely small amount of current, very high voltage. So getting back to the Leyden jar, this is what they did, and they had all kinds of schemes for different methods of rubbing. They found out that certain animal fur worked better than other animal fur, and a sulfur ball was really good for collecting one kind of charge. And what they would do, the Leyden jar is just a big jug sitting here, and they would transfer that static electricity into a rod coming out of the top of it. Well, in short order, they learned that if they could charge the thing up, but if it was just a piece of wire sticking out, like a sharp-pointed piece of wire, it wouldn't last very long. And, well, why is that? Well, it's called the point dissipation. The electric current flowed out into the air. So the solution is to put a ball on there of a certain diameter or large diameter, and I expect that if you've seen pictures of antique Leyden jars, they always have a rod sticking out of the top with a ball on there. Well, what that does, it prevents or it retards the flow of the electrons off into the air. And this was their solution. Now, later on, they did a lot of other things, but at this point, my note says I need to do a little demonstration for you. I have a thing here called a negative ion generator, and we tried to see if we could see it with this camera here. Inside these little copper tubes, there's a bunch of really sharp-pointed nails, and there's a little power supply on here. It's a 7,500 volt power supply. And there, you have to take my word for it, there's a bunch of tiny blue dots in there at the tip of each nail. And what I wanted to show you is that Franklin was right about the silent current. There is electric current flowing off into the air. Some people find it hard to believe that electricity would flow out into the air. And I have to handle this thing carefully because it'll shock me if I don't. But do we have, I don't know if we have a camera, if you can see this. But at any rate, watch the candle flame. Now, that's not air blowing, that is negative ions coming off of those points, pushing that candle flame over. And it's quite effective. It's estimated that each sharp point can have about 2 to 10 milliamps maybe a little bit more, 4 to 20 milliamps of current flowing through there. Are you getting that up there on your camera or not? No? Okay. Anyway, I think everybody can see it almost blows the flame out. I'll see if I can get it to blow it completely out. I don't know. Well, it'll almost blow it out. There, got it. Okay. Ions blew the candle out. Now, why is that important? Well, that was the principle of the Franklin lightning rod, because some of these lightning rods, they would put fancy decorations, brass balls and spears and things like that on there. However, those things were mostly, they found out later on, ornamental. The important thing was the sharp point on the top. Now, Franklin's rod, there was only one thing wrong, and it was because he didn't recognize that each sharp point is limited in the amount of current it can handle. If you could put 100 lightning rods on the top of a house, it's going to carry a lot more current off, discharging this electric field that's above the house. Different people will tell you different numbers on these things, the current, but the main thing is there is electric current that flows into the air. Now, we'll get into what we can do to protect ourselves. I think everybody has an idea of where the lightning came from the cosmic rays, and how they charge the clouds. I hope I explained that. One of the things that we do today, and almost everybody, I'm going to say not everybody, but almost everybody has a computer. Most people have hi-fi equipment, audio equipment and such. All of that stuff is all solid state now. Solid state electronics works at very low voltage levels. And so as a consequence, it's more vulnerable than the old tube stuff. You know, tubes operated at several hundred volts, and transistors operate down 2 or 3 volts, sometimes less. It doesn't take very much voltage to ruin a transistor. What we do, we buy surge suppressors. And you go in Radio Shack or any discount store, and we plug our equipment into the thing, and we say, we have faith in this thing. It's going to protect my computer, radio, or whatever. However, the way they work, it's called a metallic oxide varistor. And they effectively, if a really high spike comes in on your power line, it clips that off below the point where that will come in and do internal damage into your electronics. It works pretty well. The only thing downside is they wear out, because each time they clip off a transient like that, it's going to take a little bit of their lifetime. There are, over the years, there have been 3 basic methods for trying to trying to protect ourselves and our property and our houses, businesses, and everything from lightning. The first one is the Franklin rod, and I'm speaking of technology nowadays. And I don't know if you know what NFPA is. NFPA is National Fire Protection Association. And a lot of big buildings, if you look at the top, you will see some spikes sticking up 18, 20 inches long. If there's a peak roof on the building, these spikes will be along the peak at 10 or 15 foot intervals. Then it'll be around the periphery of the building. And then if you looked really closely, you would see they're all attached, connected by a big copper wire that's about as thick as your finger. And the intent on these things, the idea about how they work is we hope that a lightning strike would hit one of those rods. It will come down to that fat copper wire, then go down the side of the building and go to ground rods and get rid of it that way. And they work fairly well. And the fact is that they do have multiple points sticking up there. A typical large building might have 18 or 20 or 30 or 40 of these things sticking up. So that's their premise. Bear in mind, they hope to direct a lightning strike to ground. Now, there's a newer technology called ESE, and it's called early streamer emission. And I have a couple of pictures. Maybe we can, yeah. Does that look like something from outer space? These are quite interesting gadgets. They are becoming very popular, already have become pretty popular in Europe and the East. You get on the internet and you track these things, and people all over the world, mostly other than the United States, are really installing these things. Now, the original ones, and these go back some 20 years or so when the first ones came out. The original ones, the idea, what they did, they put some radioactive material at that tip on there. I'm going to show you a different one here that might help. This is a different manufacturer, same idea. And, well, I know, the camera won't focus. Sorry. That's as good as it'll do. The idea on this is, back there when they were using radioactive material, and I say back then, the early ones began by using radioactive material at that tip with the idea, that work? I don't think so. Okay. We just never could get it to come in a while ago. Oh, okay. Okay, while John's doing that, I'll continue. The idea was, if we put some radioactive material on that tip up there, okay, all right. We put some radioactive material, and this one here, John, if you could take this one. Yeah. Yeah, that's a little better. Now those things, that one right there.
Yes, sir.
Yeah. Well, it's got too much light. It's washed out. Yeah. But it's a little over a half a meter tall. To give you an idea, the ground thing is number 4, and the part 3 it says accelerator and atmospheric electrodes, and nobody I've talked to knows what that means. Atmospheric electrodes. It's impressive as the dickens. Part 2 says the ion, and number 1 up there is the air terminal. Now, to get back to the idea is, if this worked properly, we would put some radioactive material at the point. During a storm, this would cause an ion stream to go up in the air. Now, the ESE means early streamer emission, and the way lightning works, you have a streamer from the earth and a streamer from a cloud, and normally this one from the bottom is positive and the top one is negative, and they meet, and then you have a lightning stroke. The bottom one is formed from St. Elmo's fire. If you remember St. Elmo's fire, it's the positive charge that comes up and the negative charge comes down. Now, this sounds like a good idea, and their intent is that let's do, if we can't stop lightning from happening, what we will do is put these things out there, and we will control where the lightning strikes instead of just randomly throughout the area. And so if you read about them, they say we put them at certain intervals around here, and if the voltage does get up, this 12 kilovolts per meter, if it gets high enough to strike, we will cause it to strike this thing instead of something of value, the power lines or your antenna or your house or anything. This sounds like a good idea, except almost all thunderstorms have wind. And if you have wind, it's going to push that little batch of, that helped. It's going to push the ion cloud away. It doesn't take much. The ions are very light, and a little bit of wind will carry them away. Now, somebody said, well, this is not good. We're polluting the atmosphere with the radioactive material. We don't want to do that. So they came up with this other one. Can you put the other one? Yeah, that one right there. Now this one, if you look at the tips up there very carefully, it looks kind of like a spark plug. And their idea is what we will do instead of radioactive material, we'll have a little power source and we will generate a spark. The spark will ionize the air, which it does, and then that will go up. And the problem is, to go up to a cloud, it would have to go straight up for hundreds of feet, I suppose, to get up to the point where you would initiate the lightning strike. And again, the wind blows all the time. And so I'm not sure, I'm saying I'm a skeptic about these things. 3 or 4 years ago, a guy came in, the oil and gas industry has terrible lightning problems up where we are. One of their people came in with one of these things, and it was cremated. It was burned to a crisp, and I don't think it was this company. These are made by a company in France called Dielectric. I think this was another one, because there's quite a few of these things being made in Europe. Actually, these are from France. At any rate, this thing was cooked to a crisp, and at that time, none of us knew what it was. So then I had to start doing some digging on this ESE business. Now, like I say, the wind affects them severely. Now, I'm going to get to my pet. See, what I've been manufacturing for 26 years works on an entirely different principle. It works on Franklin's principle of the silent current. Instead of having one sharp point sticking up in the air, we put a lot of them up in there. Now, this thing right here is an example. These are stainless steel wires that project up in the air. This little brush is what it looks like before we flare this out. And up in San Juan County, there's a great big gas and oil field, and there are several thousand of these in service right now. protecting automated well sites. And the oil and gas industry over the, oh, okay. Yeah, okay. It's not complicated. That's a big crimp plug right there, you can see. There's the crimp plug. And we crimp a bunch of stainless steel wires in that lug, and then we provide this little stand. And to protect an automated well site, a lot of them have no AC power. They have solar panels and batteries. And they're the ones that are most vulnerable, because when the humidity is really low, when it's less than 10% and the wind is blowing and it's hot, static charge will accumulate on the whole, everything they've got. It'll accumulate on there, and static electricity will build up to the point where it'll break down the components inside. The RTU is RTU is a little mini computer instrumentation processor that talks back to the home office via cell phone. They used to use UHF radio, now they use cell phone. But they're very vulnerable. The RTU is very vulnerable to high voltages, and static electricity was killing these things. And so that's why most large companies, ConocoPhillips and BP and all those, they put these, that just goes on automatically when they put in a new automated well site. They come and get bundles of 20 or 40 at a time and put them on there because they know they work. Now, if you go on the internet and read about this method, research it, a lot of scientists will tell you that this doesn't work. And the thing is, the proof is in the pudding. If it didn't work, I wouldn't be making them for 26 years. We give a 1-year guarantee on everything, and I have not had to eat any of these things. We make a big rugged thing that, in fact, on the front of your program, there's a picture of a big rugged thing mounted on the beacon light of a large tower, and that is called an eagle's nest, and that's a huge thing with stainless steel 1/8-inch spikes sticking up, and we have those on radio and TV towers up to 2,000 feet tall. And I will say that if you protect the top of a big tower like that, if you don't protect the sides, you're going to get a side strike, because what that does, it dissipates the field up around the top, but then the electric field will mold around it, like I showed you with the isoelectric lines. It'll come in on the sides, and we learned the hard way that a lot of antennas would get, side-mounted antennas would get hit. So that's my pet. It works on the principle of this little negative ion generator and the candle. Whenever there's a strong electric field above it, the first ionization potential is nominally around 10,000 volts. You think, well, we're never going to get 10,000 volts on this thing up in the air. Yes, you will, because if you put this up, let's say we have a 50-foot tower, what's nominally 15 meters tall, and if we have 10 kilovolts per meter, then we've got 150,000 volts by the time we get to the top of that tower, and that will initiate the 10,000 volts that it takes for this to work. And so what it'll do, I'll draw another picture of the isoelectric lines here. What they do in this circumstance, and we will assume it's only on the top. So assume we've got dissipation up here on the top. What will happen is these lines, where they were close to the top, now you will find, if you could see them, they would balloon out like this. And this means that the field is much less intense here, and so the top of your structure is protected by this. So in this case, it's much more likely you'd get a side strike coming in this way than up there on the top. And everybody says, well, lightning's supposed to hit on the top. No, not necessarily. Now, I wanted to speak about how we measure lightning energy. You know, they always talk about volts and amps and watts and things like that. The real measure that atmospheric scientists use is called the Coulomb. And a Coulomb is a definition, it's an old definition, that is 1 ampere for 1 second flowing past a point. You can take a piece of wire and you say, well, if I have 1 ampere flowing through that wire for 1 second at a time, and it's even a quantity of electrons. It's a huge quantity of electrons, but it is a specific quantity of electrons. Now the example is, let's say if we had a 120 watt light bulb, and we have 1 amp, if we put 120 volts on it, 1 amp is going to flow through it. Well, that means that every second that light bulb it's going to take 1 coulomb of energy to light that light bulb. And in a minute, it's going to take 60 coulombs to light it for 60 seconds. Now, what I'm leading to is lightning itself. People assume, and of course you always get you in trouble to assume things, they assume that I know I read something one time, a long time ago, they assumed that it was 1,000 coulombs. Well, the researchers in Florida say, oh no, it's on the order of 5 to 20 or 30 coulombs. And so you say, well, you're telling me that the amount of energy that it took to light that light bulb for less than a minute causes a lightning strike? Yes, and the reason why is the lightning strike occurs in a matter of microseconds. Typical lightning strike is 30 to 50 microseconds. Now, if you take that same energy, let's say if you had 10,000 amps and you integrate it out over a few minutes, you're going to wind up with milliamps. And that's the way these things work, is milliamps flow from these points. But if you have a lot of them in parallel, you can have up to several amps flowing from the top of a structure. And it's been measured. There's a large television station in Los Angeles, KRON, and they insulated their tower somehow, and how they did it, I don't know. Well, maybe they insulated the dissipator on the top of it. But they measured several amps of current flowing through there when storms came over. And so what my point is instead of having 10,000 or 20,000 amps for a few microseconds, now you've got 4 or 5 amps integrated out over several minutes' time. Same energy, low voltage, low current, and no damage. Now there's some people assume that this method causes the lightning strike to strike somewhere else. It moves it over to the neighbor or something. Absolutely not. It does not do that. It actually dissipates the field, the energy out of the field by dissipating it out in the air by this means, rather than taking a big strike. I think I'm running late. How am I on time here, John? I may need to speed up here a little. Well, I need it, if you know about radio receivers, there's a thing called signal-to-noise ratio. And what that amounts to is if you have high ambient noise, you have a poor signal-to-noise ratio, which costs you on your receiving. Several years ago, quite a number of years ago, some of these things were installed, we didn't manufacture them, but they were installed out at an Air Force base in California, and Air Force still uses a lot of HF radio. And because these things, actually they prevent corona from forming on sharp points, they dissipated at a much lower, sir? What are we? Oh, no. I was wondering how much time I have. Huh? What I want to know is how much time I have left. I don't need that. I don't even know what it means. So my point is that it by preventing the corona from occurring from tops of towers and things like that, the Air Force claimed it reduced their signal to noise about 20 dB. To non-technical, that's absolutely meaningless. But KOB, which is a big radio station here in Albuquerque, they went to 50,000 watts in 1941, and they learned that because they didn't account for corona on their guy wires, when there was high wind in Albuquerque, it would flash over, and they had to reduce the power on the transmitter. And they had to take it down to half power and sometimes less to stay on the air. Well, after that, they realized what the problem was, and they were able to fix it. Scientific testing. Of the 3 or 4 methods outlined above, and one thing I didn't mention was the blunt tip lightning rod. I'm not even going to get into that because I think it's a mistake. But the question is, of all the previous methods that I've described, how many have been scientifically tested by a qualified and unbiased lab or testing agency? The answer is 0. Nobody has ever done bona fide, valid, unbiased tests on this. And yet there's a lot of politics in it. And somebody will say, well, this method's no good and that method's good. But it's not based on science. It's based on personal opinion and politics. Yeah, I say politics, both government and business. Business politics can be dirtier than government politics. I'm going to give this talk to a group of amateur radio operators, 2 weeks, and part of it's addressed to them, and you can do it yourself. Now, I've been manufacturing these things for 26 years, and so why would I tell you how to do it yourself? Because I'm bailing out. I may sell out sometime in the not too distant future, so I don't need to sell these things. But to do this, do it yourself. If you had a radio tower or some flagpole or something like that, all you need is some stainless steel wire and some hose clamps. And you just cut you a bunch of stainless steel wire and you clamp it to the pole and flare it out like this, and you will be amazed how much it reduces the problems. We live on a mesa outside of Farmington, been there for 36 years, and we used to have severe lightning problem on top of this mesa, and it's gone because I've got enough of this protection up there. The taller the structure, obviously, the more dissipation you need because it's penetrating deeper into the electric field. And the wire that I mentioned, all you need is something like number 18 or whatever. These things, we have protected quite a number of barns and houses. We make a different kind of bracket that goes on the peak of the roof. Now, they all have to go to ground. This does not work by itself. It has to have a low resistance path to ground. But there are quite a number of houses, barns, warehouses, oil storage tanks, including fiberglass tanks, believe it or not, water tanks that have this on them. And one of the things that I have done is to, if you have a lot of space around your property, if you have a big yard, you can put these out in the yard and they will help to dissipate the field, the electric field in your yard. And finally, I'm working on a product now that I'm trying to get some assistance in testing it, but for some reason these labs, I went to Sandia Lab, I went to Los Alamos, and Los Alamos awarded me a $20,000 thing. They said, well, you don't get the money, but you get $20,000 of work. And it was worthless. It was absolutely worthless. The guy did a computer simulation, and he used 10 watts of power as a rating. You can't rate lightning with 10 watts. It's and so I'm still working on it, but I have another idea that rather than allowing what happens when lightning hits a power line, an AC power line, it changes. If it hits the wire, it suddenly becomes an electromagnetic pulse. There's this huge charge deposited on the wire. It's all the same polarity, so it splits in 2 halves and it takes off in opposite directions down the wire. Now, if your house is a half mile downstream, it comes down the wire, and having worked in the power business, I know that the neutral for the power goes right around your meter pole, or your transformer pole, and right to your meter pole, and so they effectively let that electromagnetic pulse from that lightning strike right into your house. And I'm working with the Farmington Electric Utility. It is a municipally owned electric utility, and they like these ideas, but I have to get further along. But the idea is we would use, an electromagnetic pulse has an effective inertia. It doesn't have enough mass to have physical inertia, but it generates a huge electromagnetic field around it that keeps it going in a straight line. It doesn't want to turn. And so I'm taking advantage of that to where the wire turns to go down a meter pole we'll put a device there, and it's similar to this, but much more heavy duty, and it will take that electromagnetic pulse, the energy, right out in the same plane and dissipate it in the air. You will have a sudden puff ball of plasma. The air will turn into a plasma ball, and the reason I know that I know it's plasma because we have had nighttime reports of seeing our equipment operate out in the oil and gas industry. It's a funny. I'll just really be brief. But there was a truck driver came in one time and he said, "I saw some of these things out in Hart Canyon and they were all glowing blue." And there was one of our employees. I thought he was going to faint because he thought they were burning up. I said, "That's perfect. When these things are working at night, you will see a blue glow. Blue glow above here." And that says you're ionizing the air just like the little blue dots at the tips of those nails. And the current flows out into the air. So a few milliamps per each one. And that application happened to be a large major pipeline that I believe belongs to El Paso Natural Gas, 30-inch pipeline. And we solved a problem for them because a lightning storm would close the control valves on this 30-inch pipeline, and that's really serious for a gas company. To close a 30-inch pipeline instantaneously. Well, I point out that everybody has a lightning story. Everyone is different. I have heard dozens and dozens and maybe hundreds of lightning stories, and everybody wants to tell me about them. I don't want to hear any more. If you have one that you would like to tell me, find someone else. Okay, I'm ready to wrap up. Am I out of time or close to it?
Okay,
you don't even know.
you have about another 35 to 40 minutes.
35 to 40 minutes? Well, I don't have any more material. Can we wrap this up? Because let's take a question and answer thing, and then that will allow the next presenter.
Yeah, you have about 30 to 40 minutes. If you want, we can do Q&A, and if you want to end early, that'll be fine. That'll help us get back on schedule. Okay, we can do Q&A. The same rules apply. You want to ask a question, raise your hand, and I'll bring the mic to you. Who wants to bring it in? Ask any question except about a lightning story.
Well, this is about lightning, but a little bit different. A few years ago, NASA had an experiment where the space shuttle towed a line behind the space shuttle. It's a couple miles long. It collected almost 500,000 volts on that line before it exploded. And in a way, it kind of proved Tesla's theory about the Earth being a sort of a dynamo. Mm-hmm. And they discontinued the experiment after that. Do you know about this, or do you have any opinions about that?
I'm having difficulty. There's echo in here, and I can't quite understand what you're saying.
I'll try it again very carefully.
Okay.
A few years ago, NASA did an experiment where they towed a line, a conductive line, behind a space shuttle. It was about a mile and a half long.
Okay, now I got that. All right.
And then it collected about 500,000 volts of electricity before it exploded. The idea is it actually showed that Tesla's theory about the Earth being a dynamo was in fact correct. They since canceled the program with that experiment. I was wondering if you knew about this or had any thoughts about that.
No, I don't know about that. I know that is one of the 6 sources of energy. It's about the lowest. The biggest one is, of course, cosmic rays, and then solar wind. There are 6 sources, and the dynamo effect is about the least important. I hate to say that, but it's about the least important. Go ahead. Yes?
Yes, sir. I was wondering, the conductor from the array, in other words, at the tip of your probe, your atmospheric electrode, I've seen a lot of braided, what I would call an air braid type conductor that leads to the ground. How important is that compared to, say, just a braided conductor?
And what's the other kind other than braided?
Well, I call it air braid. I don't know the technical term for it. But
like Litz wire or something?
It looks like a braided wire. Actually a multiple strand of wires that is braided, but it's got air
individual conductor?
Well, there is an old wire called Litz wire, which was very flexible and it had space around it. It was often wrapped around a cotton thread or something like that, cotton string, but I don't know that. Now, as far as getting the conductor to ground, we're only talking about DC current. And one of the things that I failed to mention that I'm glad you brought up, or I thought of here, is that some of these lightning people think that the field occurs instantaneously. In other words, what will happen is the reason that this fails, they claim, is because there is a sudden field above it. That's not true. As a storm approaches, the field builds up slowly. Bear in mind it was negative to positive, and as the storm approached, the field is I know I've measured it as far as 40 miles ahead of the storm. And so what it does, it inverts it from the field from the earth to the cloud bottom. But by the time, so what happens is, as soon as these things reach the ionization potential of the air, they will begin to conduct. But all it is DC, and there's nothing fancy about it. And bear in mind, it's typically in the milliamps. Now, people ask me what size wire to use. Well, number 12 or number 10 or something like that, mainly for mechanical strength. It needs to be strong enough so it'll survive. Now, people get concerned about these things mounted on a tall broadcast tower. And they say, should I have a copper wire from the dissipator down to the ground? I said, provided you have good contact to the tower steel, and at the bottom, the tower steel has a good ground, and I don't mean just a small ground. You need several 8-foot ground rods spaced out around there to give a good low resistance ground. That's fully adequate because we're not carrying massive current. We're carrying, I think the KRON experiment was like 4 or 5 amps. We're not carrying huge current. And so as a consequence, I don't think you need special wire just good old copper wire is fine for this, whatever, TW or something like that. Question?
Yes, if lightning hits a large body of water, does it create a lot of hydrogen? And if so, is there any way to capture the hydrogen?
Well, bear in mind, I don't think it does, and I can't say that for sure, but we're not talking about a whole lot of energy. And people say, well, it took 10 million volts and 15,000 amps to do this, but it only lasted for 30 or 40 microseconds. And so there's not enough energy there to really do a lot of hydrogen release for this. Yes, sir.
What's happening now with all these metal-covered buildings, pole barns? I don't see lightning rods above them, but will that be an attractor for lightning?
Well, a pole. One thing about you're talking about a large flat roof or low-pitched roof.
I live in an old mill. It's a couple hundred years old, and I covered it all with metal.
Oh, okay.
And it's up 60 feet high. Before it was covered with wood.
Yeah.
But I'm wondering if that is an attractor for lightning.
Well, it could be, and the reason I say that, remember we've talked about capacitors here, and a large sheet of metal really does fine for forming one plate of a capacitor. What I would suggest, let me ask you this, have you grounded this building at several points? No. I strongly recommend that you put some ground rods. If it's a big square or rectangular building, maybe one at each corner, and ground the metal.
I'm sure it conducts uniformly across the whole building because of the metal contact from the ground all the way up.
Yeah.
But then I haven't grounded it down at the bottom. It should be grounded into the ground.
Yes. And I mean some really good ground rods, like the 8-footers. And talking about flat metal roofs, the Navy back in the East Coast, back in the 60s, I believe, they built some big munitions buildings, and they were big flat roof buildings, and they were low. They were only 15, 20 feet high, but they were huge. And they were having trouble with lightning hitting them and causing the munitions to explode. their solution was to put on a Faraday screen. Now, a Faraday screen is just, you put a bunch of wooden poles alongside the building and you put this grid of wires over the top, and they use really big wires, and connected them all together, and then they went out and they had ground rods going down to ground. Now, this protected the buildings. In other words, the lightning would hit the Faraday wires rather than the metal of the building. However, as it traveled out, when it got to that sharp turn downward, the inertia, effective inertia, and it's not physical inertia, it's electrical inertia, it caused secondary strikes. Would go out, you know about this. Okay, they would go out sideways, and they could zap someone or do damage.
Right now, the building is not grounded. The metal doesn't go to the ground because there's a rock foundation. Would it be more of an attractor if I grounded the metal?
Well,
or would it be safer?
I'm not sure. Not having seen the building and or any know any of the details about it, I don't know.
Okay, well, I appreciate that, but maybe because the issue has come up, maybe I better get a hold of somebody that's familiar with metal buildings and see.
I think that's a good idea.
I appreciate it.
Yeah, okay.
Have you come across any estimate of the resistance or capacitance of that distance between the ionosphere and the Earth's surface?
Oh, I've got some books on that subject, and
you recall any estimates offhand?
I can't tell you numbers, and like I say, I avoid numbers in this because it's so variable. And you have to bear in mind that capacitors, the closer the plates are, the higher the capacitance. And whenever they're 120 kilometers or 100 kilometers or 200 kilometers apart, you're not going to have a whole lot.
Really?
And see, there's what's called the Earth circuit, and people have modeled it. And for instance, you're in a big flat area and the weather's nice. You have this very tiny current going upward. Then it accumulates in storms, and then they say it comes down over here, so it balances out. So what current goes up here comes down in the thunderstorms, and it's a balance. But as far as the actual capacitance in there, I don't know. But it's generally the energy's in coulombs. That's become the standard of for the atmospheric physicists. The coulomb is the measure of the energy, and not volts and farads and things like that.
I've seen one estimate of approximately a quarter farad over that distance and maybe 200 ohms. Does that sound right?
Yeah, I could buy that. A quarter of a farad, yeah.
A quarter of a farad, that's a
big capacitance.
That's a lot of capacitance.
Yeah. And what did you say, 200 ohms?
And 200 ohms as resistance.
Yeah, because it is conductive. And it's all in parallel, of course. It's a gigantic area.
This wire that's shot up with a rocket?
Yeah.
It's just a thin wire?
Yeah.
That explains why Benjamin Franklin didn't get killed when he was flying his kite with a key, right?
Well, I'm not sure about that. If Franklin's wire burned in two, then that would explain it. But the intent of these what's called triggered lightning experiments, and the little rocket is about the size of a baseball bat. And it has this, you know how a spinning rod works, the string comes off of a spinning reel. They have this thing on the bottom, and it's attached to ground, and they fire it up. And this little wire is probably 18 gauge or smaller. And it's flexible. It's stranded, very flexible wire. And they say typically the lightning will fire within 100 or 200 feet. It doesn't take very long, because whenever you have 12,000 volts per meter, and the thing gets up 100 or 200 meters, it doesn't take much to go ahead and trigger it and to fire it. So, yes, sir.
There's an alternative energy technology called solar wind farming, and this is where you use a Tesla tower, her namesake, maybe 300 feet high, pulsed at 1 million, maybe 5 million volts at the Schumann frequency, and you're essentially farming
solar wind, and you do it at dawn and dusk. And the question is, as I understand it, pretty much an inexhaustible supply of current. And familiar with that? Are the numbers big? How many would it take to run the planet? Anything that you've looked into there?
What's your question again?
Have you looked into that?
No, not really. I've read about it, but I haven't looked into it. There's one back there, John. But the thing is, people have assumed that there's massive energy in lightning and this sort of thing, and even in the solar wind. The energy level, we have an expert on solar wind here, Sumant. He worked for NASA under contract for a while on solar wind. And there's not a big, massive amount of energy coming in there, and there's certainly not in the electrostatic field from lightning. It's just not much. Was there another question?
Yes, out in California, we've had over 1,000 fires caused by this whole blast of what we're calling, some of the papers are called freak lightning. Other sources were calling it dry lightning. There were, in other words, these lightning strikes causing all the fires were coming out, many of them were coming out of a clear sky.
Yeah.
Could you comment on,
Yeah.
it's cloudless, right? So could you comment on that and what do you think was going on?
The old name is the bolt from the blue. And that's an old term, the bolt from the blue. And people have observed for several centuries that from time to time there will be a lightning strike come down from a perfectly clear sky, no clouds. All it tells us is there has to be a big electric field there. Now, whether it's in advance of a storm or something else has created that electric field, and then that's where it comes from. Now, is this in the vicinity of fires or downwind from fires or anywhere around there like that?
Was caused fires.
I know it's causing the fires. My question is were there already fires there? Not. Okay. The
It's
reason
like all in, I think, 1 or 2 days. It was this
Okay, I ask that is, smoke is heavily ionized, positive ions, and you can, well, they've taken photographs looking down in volcanoes, and there's massive lightning down in there because of the smoke of the volcano. It's positive ions, and so there's a fair amount of energy, enough to trigger these lightning strikes in there. But as far as the bolt from the blue, I've read several things on that, and they say, well, all we can say is there had to be a big electric field, but we don't know how it got there.
Sorry, go ahead.
Go ahead.
Well, what about the charge coming under the electric universe sort of model? If you've got charges basically breaking through, leaky capacitor from the ionosphere, being collected from the sun.
Now there's why I can't answer you. Of course, the whole universe is electric, but then what we deal with mostly is just down in here, in our capacitor, and we're talking about from the Earth to about 100 to 200 kilometers up. It's not a great big space, but and so what I'm saying is that I just can't tell you, but it's happened. It's been recorded on many times of a bolt from the blue comes down and has a lightning strike.
Thank you.
Yeah, the NOAA now keeps a database of all lightning strikes in certain areas, and portions of California are in that, and they said that 2.1 million acres were burnt last year from 3 lightning strikes that occurred in clear air. There was no clouds or precipitation or smoke.
Yeah.
Ron Nott, thank you very much.
Thank you.
Okay, we're going to have a very brief intermission, about 5 minutes. If you want to see Ron in the back, you can go there. And we're going to try to come back, and next up is Harvey Fiala.
That's what I was going to say.